What does a speedometer, climbing a mountain, and finding the steepest point on a curve have in common? They all involve differentiation, one of the most powerful tools in mathematics. Let's discover what it really means. Imagine you're standing on a curved hill. How steep is it exactly where you're standing? For a straight line, finding slope is easy, rise over run. But curves are tricky. The slope keeps changing. This is the problem differentiation solves. For a straight line, we can easily calculate slope as rise over run, but for curves, the slope changes at every point. Let's start with what we know. Between 2 points on our curve, we can draw a secant line, just a fancy word for a line cutting through the curve. The slope of this secant line is the average rate of change between these points. The slope is rise over run. The rise is f of x plus h minus f of x, and the run is h, the horizontal distance. Here's the key insight. What if we make h smaller and smaller? Watch what happens as the second point gets closer to our original point. The secant line starts to hug the curve more tightly. It's becoming a tangent line, a line that just kisses the curve at exactly 1 point. If we zoom in close enough, every smooth curve looks like a straight line. The slope of that line is what we call the derivative. This gives us the formal definition of the derivative. The derivative of f at x, written f prime of x, is the limit as h approaches 0 of this fraction. We're not dividing by 0. We're asking what value this fraction approaches as h gets infinitely small. We can also write this as di dx or df dx, representing the instantaneous rate of change. Let's put this into action. We'll find the derivative of f of x equals x squared using our definition. Following our process, substitute, expand, simplify, factor, and take the limit. We get the derivative of x squared is 2x. So the derivative of x squared is 2x. This means at any point x, the slope of the curve is 2 times x. Let's try one more, finding the derivative of x cubed. Following the same process, substitute, expand, simplify, and take the limit. We get the derivative of x cubed is 3x squared. Notice at x equals 0. The slope is 0. The curve is flat. At other points, the slope depends on x squared. Notice the pattern. For x to the power n, the derivative is n times x to the power n minus 1. This is called the power rule, and it makes finding derivatives much faster. But remember, this comes from the rigorous limit definition we just used. Why does this matter? Imagine a car whose position is given by s equals 5t squared, where t is time in seconds. The derivative gives us velocity, how fast the position is changing. Using the power rule, the velocity is 10t. At t equals 3 seconds, the car is moving at 30 meters per second. The derivative transforms position into velocity. Let's recap. Differentiation finds instantaneous rates of change by taking a limit. Geometrically, it gives us the slope of the tangent line. Algebraically, we use the limit definition or shortcut rules like the power rule. And practically, it helps us understand how things change, from motion to growth to optimization. The derivative is your mathematical microscope for understanding change. Master it, and you unlock the power of calculus.